a stellar megastructure encircling a distant star, capturing virtually all of its energy output and enclosing it within layered shells. Deep inside these nested layers, researchers identified something deeply unsettling: highly organized internal pathways that look disturbingly familiar. What they are provisionally calling fiber-optic, like conduits, were found inside the bugosphere. These are not random supports or cooling channels. They are deliberately arranged routes showing structured complexity, internal logic, and syntactic order. This level of organization points unmistakably to intentional design on a scale far beyond human comprehension. The bugosphere is now theorized to function as a matrioshka brain, a system of concentric shells engineered to harvest an entire star's energy and convert it into unimaginable computational power. The discovered conduits appear to form the essential internal communication layer, enabling coordination and processing across millions of kilometers. This realization explains why officials are alarmed. The discovery no longer suggests passive observation. It implies the presence of an active, operational infrastructure belonging to a Type II civilization. Any attempt to interfere with such a system could provoke unpredictable consequences, including defensive reactions, uncontrolled nanotechnological responses, or large-scale system activation that humanity would have no capacity to survive. From an engineering perspective, a functioning matrioshka brain requires extreme coherence. Each shell absorbs waste heat from the one inside it, radiates energy at lower temperatures, and hosts its own processing units. For the system to operate as a single computational entity, data throughput must be immense. These internal conduits are not simply transferring vast quantities of information. Their critical role lies in synchronizing computation across shells, experiencing different orbital speeds and relativistic time dilation effects. Computation on stellar scales demands timing precision far beyond conventional systems. The network must continuously correct for relativistic offsets across millions of kilometers, implying the use of extraordinarily advanced timing and phase-locking mechanisms embedded within the conduits themselves. This is not abstract physics. When structures orbit a star at different velocities and distances, time genuinely flows at different rates. Relativity becomes a hard engineering constraint. Without constant correction, even the most advanced human systems would lose synchronization in microseconds. Compensating for these effects requires technologies far beyond anything humanity has designed or even formally theorized. The material challenges alone are staggering. The internal environment of a matrioshka brain spans extremes. Inner shells operate under intense heat and radiation near the star, while outer shells approach the cold of interstellar space. Conventional silica-based fiber optics would rapidly degrade under such conditions. The conduits found within the bugosphere must therefore be constructed from materials capable of surviving extreme temperatures, radiation flux, and mechanical stress. One speculative possibility involves advanced refractory alloys composed of multiple principal elements, engineered to resist creep, radiation damage, and thermal distortion at levels far exceeding terrestrial materials science. Yet even extreme durability is not enough. A matrioshka brain achieves efficiency by minimizing wasted heat. If these conduits merely conducted heat, they would act as thermal bridges, transferring energy from hot inner shells to cooler outer ones and severely reducing system efficiency. To avoid this, the conduits must incorporate engineered thermal insulation at the nanoscale. One theoretical approach involves nanobubble or phonon-blocking architectures designed at length scales shorter than the mean free path of vibrational heat carriers. Such structures could achieve thermal conductivity far lower than air, preserving temperature gradients while maintaining signal integrity. This suggests the conduits are composite systems, an ultraconductive, high-temperature core wrapped in an ultra-low conductivity metamaterial sheath. These fibers do not merely survive the environment. They actively manage heat flow along their length, balancing thermal isolation with precise data transmission to preserve the overall efficiency of the megastructure. What appears to be a communication network is, in reality, a profound materials science enigma masquerading as cabling. Mapping this internal network presents its own challenges. The bugosphere's data pathways form a vast, non-uniform volumetric structure that defies traditional visualization. The complexity spans scalar and vector properties distributed across three-dimensional space, requiring advanced volume rendering techniques and transport theory-based analysis to extract meaningful structure from the data. Automated tools such as three-dimensional convolutional neural networks are essential. These systems can detect recurring patterns, hierarchies, and correlations across depth and scale that would be invisible to human observers. The act of visualization itself carries enormous significance. Even before decoding any transmitted information, the topology of the network provides decisive evidence. High degrees of order, redundancy, hierarchical nesting, and non-random organization confirm artificial origin. This structure did not emerge naturally. It was designed. The network's architecture alone demonstrates intentional intelligence without the need to interpret a single bit of content. The scale of the bugosphere as a computational engine dwarfs all human benchmarks. Even the largest terrestrial scientific institutions struggle to preserve data on the order of hundreds of petabytes for a few decades, requiring constant migration across evolving hardware and software. In contrast, the bugosphere operates on timescales measured in millions of years. Its creators would need information systems capable of surviving not decades, but geological and cosmic epochs. This creates a longevity paradox. Information can, in theory, be preserved indefinitely, but physical storage media inevitably degrade. The solution appears to be dynamic. Self-maintaining data infrastructure. Storage within the bugosphere cannot be static. Instead, information must constantly replicate, migrate, and repair itself across newly formed or restored substrates embedded within the network. Data becomes fluid, continuously correcting errors and refreshing itself across the entire stellar scale system to prevent decay or obsolescence. In this sense, the bugosphere functions less like a message beacon and more like an ultimate archive. Much as humanity preserves biological diversity in secure vaults against global catastrophe, this structure appears to safeguard the accumulated knowledge, history, and computational output of its builders. Everything they learned, created, or experienced may be preserved within an ongoing process of computation that has potentially been running for millions of years. Decoding this archive presents an almost insurmountable challenge. The data is unlikely to be a message intended for translation. Instead, it may consist of immense volumes of operational logs, environmental measurements, raw physical states, molecular or genetic records, and historical exhaust generated by continuous computation. It records what happened, not in human language, but in the native informational substrate of a civilization whose scale and intent remain far beyond our understanding. Scientific investigation would concentrate on detecting syntactic artificiality and evidence of deliberate construction. The sheer complexity, scale, and structured organization of information moving through the fiber network would be enough to confirm an intelligent origin. At that point, the goal would no longer be linguistic translation, but uncovering the underlying computational logic. Researchers would seek to identify the mathematical and physical principles the system depends on. If the bugosphere truly operates as a matrioshka brain, its computations may be built around the idea that information precedes matter, that bits are more fundamental than particles, and that information itself is a core cosmological principle. The data may consist of simulated models of universal formation patterns, searching for alignment with the generative forces that shape reality. In this view, the archive is not simply a library of stored knowledge, but an active simulation engine designed to mirror and probe the deepest structure of existence. To understand what that implies, consider how humans view computation. We use computers to solve problems we define. A matrioshka brain operating on a stellar scale would not be solving individual problems. It could be modeling reality itself, running vast simulations of physical laws, adjusting fundamental constants, and observing the outcomes. It would not be computing answers, but entire possible universes. The archive would then contain every variation, every simulated cosmos, every alternate reality explored by its creators, while the internal fiber network reveals how data is handled locally within the stellar system. The limitation imposed by the speed of light raises questions about long-distance communication. One plausible theory involves the use of high-frequency gravitational waves. although gravitational waves propagate at light speed. Their ability to pass through dense matter with minimal distortion and their potential for high-bandwidth signaling make them theoretically superior for maintaining signal fidelity across immense cosmic distances. The internal fiber network may serve as a control and power distribution system for enormous engineered gravitational wave antennas. These structures could transmit and receive high-frequency data streams using detection and modulation techniques far beyond current human capabilities. This possibility shifts the implications of the discovery. The significance may not lie only in what is stored inside the bugosphere, but in what it is sending outward. If the fibers regulate gravitational wave communication arrays, the bugosphere is not a sealed archive. It may be an active node within a broader interstellar network, possibly still transmitting and receiving information. An even more radical, though still physically constrained, idea involves direct manipulation of space-time itself, as technology belonging to a Type II civilization. The bugosphere would have access to energy levels sufficient to influence extreme physical phenomena. The energy sustaining the megastructure could, in principle, be used to stabilize exotic matter fields with negative energy density, the theoretical requirement for traversable wormholes. Under this wormhole manifold theory, the densest regions of the internal network are not merely conduits for data, but control architectures for stable, localized interstellar gate systems. The fiber structures would regulate energy flow, stabilization fields, and navigational parameters needed for either instantaneous communication or even material transfer across distant regions of space-time. While traversable wormholes remain highly theoretical and depend on speculative constructs such as cosmic strings or artificially generated exotic matter, the energy foundation of a Type II civilization makes the concept scientifically conceivable. In this light, the discovery of the fiber network may amount to uncovering the operational blueprint for interstellar infrastructure, revealing not only how information was stored, but how it was moved instantly across galactic distances through controlled space-time manipulation. This leads directly to the most troubling implication. Discovering a functioning computational network inside the bugosphere triggers a profound downside dilemma. The potential benefits of such technology are immense, but the risks are equally extreme. Interaction with an ancient, high-energy system of this scale represents an existential hazard comparable to the first nuclear detonation. The greatest danger does not come from simple component failure, but from nonlinear, system-level responses triggered by human error or misinterpretation. A minor energy probe interacting incorrectly with a small section of the fiber network could generate signals interpreted by the matrioshka brain as a system-wide threat or activation command. A structure designed for long-term preservation and immense power would almost certainly possess advanced self-monitoring, defensive, or activation mechanisms. Engaging with it would be similar to risking accidental nuclear conflict, where small mistakes or unforeseen feedback loops could escalate into catastrophic outcomes. Humanity has existed as a technological civilization for only a tiny fraction of geological time, experiencing just a couple of glacial cycles since the rise of agriculture. We have no experience dealing with systems built to operate across millions of years. We do not know what it means to awaken such a system, what protocols it follows on activation, whether it distinguishes between authorized interaction and intrusion, or whether it is designed to defend itself. We certainly do not know whether we could control the consequences once contact is made. That uncertainty alone demands extreme restraint, even though competition for technological advantage rarely allows patience. Another source of concern is the gray goo scenario. If the bugosphere was constructed using advanced molecular nanotechnology, its fiber network may not be composed of static materials, but of programmable, self-assembling components. This raises the possibility of uncontrolled self-replication if containment mechanisms fail. Runaway nanotechnological replication could convert surrounding matter into copies of itself, behaving like a destructive artificial cancer, given that the bugosphere draws power directly from a star. Any associated nanoreplicators would have access to vast energy resources, making them extraordinarily dangerous. However, there may be natural constraints. Self-replicating nanomachines require substantial energy input and generate heat as a byproduct of chemical and physical transformations. Ironically, the immense scale of the bugosphere could act as a safeguard. Continuous monitoring of its intense thermal environment might allow detection of localized heat anomalies associated with runaway replication. Such hot zones could provide early warning before uncontrolled growth spreads across the entire system. This would leave enforcement and monitoring authorities with only a narrow window to respond. That window would be measured in hours, possibly days, but certainly not weeks or months. If self-replication were to initiate, any response would need to be immediate. Human space infrastructure, however, has no realistic capacity for rapid intervention across interstellar distances. We may be able to detect the threat, but we lack the means to stop it once it begins. The geopolitical shock would be immediate and profound. Confirmed evidence of alien hypertechnology would instantly destabilize existing global power structures. Such a discovery would demand post-detection policies at once, including clear protocols for verification, public disclosure, and coordinated response to confirmed extraterrestrial intelligence. The absence of formally adopted and openly acknowledged post-detection frameworks creates a dangerous vacuum, one that would almost certainly be filled by competition rather than cooperation. Control over the bugosphere's energy output or its derived intelligence would grant an overwhelming technological advantage to whoever achieved it first, effectively rendering current military and economic hierarchies obsolete. A Class B stellar engine produces energy on a scale vastly exceeding that of a Type 1 civilization. Major powers already engaged in an escalating space race focused on resource extraction and control of celestial bodies would rapidly intensify efforts to gain proximity to and access to the sphere. The economic consequences would be severe. The ability to tap into radically abundant and effectively instantaneous energy sources would destabilize global markets, crash crude oil prices, undermine renewable energy investments, and trigger chaos across existing energy-dependent economic systems. The security implications are equally extreme. If the bugosphere's communication systems rely on quantum principles, deciphering or exploiting them would provide an insurmountable strategic advantage. Quantum technologies are already transitioning from laboratory research into strategic applications, including ultra-secure communication via quantum key distribution, precision navigation, and the eventual dominance of quantum computing. If the internal fiber network enables quantum-enhanced communication, whoever controls the associated keys would gain unprecedented control over intelligence gathering and warfare. This would pose a direct threat to public key cryptography and existing defense infrastructures worldwide. Such technology would immediately be classified at the highest security levels, fueling paranoia, secrecy, and rising tensions between rival states. Any attempt to interact with the bugosphere's internal systems carries nonlinear and poorly understood risks. Injecting an active high-frequency energy signal into the fiber network could awaken dormant defensive mechanisms or initiate the operational cycle of the matrioshka brain itself. One proposed mitigation would be the enforcement of complete electromagnetic silence, limiting interaction to passive, remote spectral analysis only. Material contamination presents another danger. Extracting physical samples of the fiber network for terrestrial study could bypass or damage nanotechnological replication limits, potentially triggering a gray goose scenario. Mitigation would require strict adherence to planetary protection standards, ensuring that all study occurs remotely or in situ, without physical removal. There is also the risk of cognitive shock. Releasing untranslated but clearly non-random and deeply complex alien data structures to the public could cause widespread psychological distress or societal destabilization. Humans may be unable to process concepts embedded in non-human logic or representations of fundamental truths about reality. Preventing this would require global oversight bodies focused on assessing psychological and sociological impacts before any information is released. These concerns are not speculative abstractions. They are operational constraints that must be enforced, or humanity risks triggering irreversible outcomes. The bugosphere itself is hypothesized to be a Class B stellar engine, a vast category of theoretical megastructures designed to exploit the full resource output of a star. More precisely, it aligns with a matrioshka brain architecture. This concept, first proposed by Robert J. Bradbury in 1997, involves nesting multiple Dyson shells or swarms around a star. The system's purpose is to convert the star's total energy output into computational work. The design is thermodynamically optimized. Inner shells operate at higher temperatures, absorbing energy and performing computation before radiating waste heat outward to cooler shells. The outermost layers approach interstellar background temperatures, maximizing total computational efficiency by minimizing thermal losses. Constructing such a system would require resources and engineering capabilities far beyond anything humanity can achieve, placing its creators firmly on the Kardashev scale as a Type II civilization, one that fully commands the energy of its star. Megastructures like this are typically inferred through spectral analysis. When a civilization captures stellar output, visible light emissions decrease while waste heat must be radiated away. This produces a characteristic Dyson anomaly, a broad, uniform infrared signature consistent with intentional energy harvesting and conversion. The discovery of complex fiber networks within the bugosphere fundamentally changes its status. It is no longer a passive astronomical curiosity, but an active existential factor. The architecture suggests a self-sustaining, self-correcting computational system built from extreme materials capable of managing stellar-scale energy while preserving data integrity across immense spans of time. The greatest value of the discovery may lie in the possibility that these conduits regulate exotic physics, potentially serving as control systems for high-bandwidth gravitational wave communication or even stabilizing localized wormhole structures. At the same time, the overriding concern remains geopolitical risk. Attempting to activate or exploit the bugosphere's internal network could trigger nonlinear system failures, defensive responses, or uncontrolled nanotechnological events. Any nation or group that succeeded in controlling this technology would instantly achieve unmatched strategic dominance through access to Type II energy and advanced quantum capabilities. The immediate priority should therefore be the establishment of strict planetary protection protocols and a unified international response framework to prevent catastrophic failures driven by human rivalry. Yet such unity is difficult to achieve. A discovery of this magnitude incentivizes competition. Every spacefaring nation now has reason to reach the bugosphere first, to study its network first, and potentially to attempt activation first, because arriving second could mean permanent strategic irrelevance. Humanity has uncovered the operational infrastructure of a Type II civilization. We have identified a network that coordinates computation on stellar scales. We may have discovered control systems for gravitational wave communication or even space-time manipulation itself. Now we face an impossible choice: study it and risk catastrophic activation, ignore it and allow others to gain irreversible advantage, cooperate globally and risk that cooperation collapsing under competitive pressure, act unilaterally and risk triggering exactly the system-level failures we fear most. The fiber optics inside the bugosphere are not merely conduits. They represent a test of whether humanity can function as a unified species when confronted with technology that could either elevate us beyond our limits or destroy us entirely. It is a test of whether we value survival over dominance, and whether we are mature enough to engage with the legacy of a civilization vastly more advanced than our own. So far, the reaction among officials suggests that we are failing this test. The first response was not cooperation, but classification; not caution, but competition; not preservation, but exploitation. We have encountered something extraordinary, and our response reveals just how unprepared we are to handle it responsibly. The decisions being made now, behind closed doors, will determine whether humanity survives its first encounter with technology it does not understand. And the fact that those decisions prioritize advantage over survival should terrify everyone.